你好. Hello. This is the 11th lesson in heat transfer. The focus of the 11th lesson is on multi-dimensional, steady-state conduction heat transfer. There will be 4 parts to this lesson. In the first part, we will look at a few relevant problems that are multi-dimensional conduction heat transfer problems. And we will also discuss a numerical technique for solving problems of these type, called the finite volume method. By the end of this lesson, you should be able to provide an example of an engineering problem that fits into the category of steady-state multi-dimensional heat transfer. You should also be able to explain why problems in this category are most easily handled with numerical solutions. On with the lesson. The focus of this lesson is on steady-state multi-dimensional heat transfer. Multi-dimensional means that temperature gradients are important in more than one direction. Up to this point in the course, we have only considered, at most, temperature gradients in a single direction. These problems were categorized as one-dimensional. We also looked at a smaller subset of problems called extended surfaces, or fins, in which, even though the heat transfer was in more than one direction, temperature gradients were important only in one direction along the axis of the fin or the extended surface. While there was heat transfer in a second direction, temperature gradients could be safely neglected in this direction due to the condition that the BO number is less than 0.1 for heat transfer in that direction. While there are a limited number of analytical solutions available for multidimensional conduction heat transfer problems, problems of these types are best analyzed using numerical approaches. Let's look at a few examples of problems that fall into this category. One example would be the cooling of gas turbine blades. In the picture on the right, you see gas turbine blades. The blades have holes and channels. In order to protect the gas turbine blades during the operation of a gas turbine, the blades must be actively cooled, because the gases in the combustion turbine often exceed the safe operating temperature of the metallic blades. The cooling channels provide for cool airflow that protect the solid material. In the picture of the right, you can see the result of a numerical solution to the cooling of these gas turbine blades. This numerical solution is similar to the one that you will learn about in heat transfer. A second example of a problem that is categorized as multidimensional heat transfer is the heat transfer in a cavity-type solar receiver. Here you can see a photograph of a cavity-type solar receiver operated in the solar furnace at Valparaiso University. Light from a heliostat, which is a sun tracking mirror, is being directed into a solar concentrator composed of over 300 small hexagonal faceted mirrors. These mirrors redirect the light to the focal point at the front of the cavity-type solar receiver. The concentrated light enters the cavity. Small amounts that do not enter the cavity are reflected from the front surface, causing the image to be washed out or very bright in this section. In this particular test, we were testing a type of technology called sodium heat pipes. You can see the top of the sodium heat pipe extending through the cavity-type receiver. The surface of the heat pipe is red because it is at over 1000 degrees centigrade. We were interested in modeling the heat transfer in this cavity receiver, and we applied a numerical technique to do so. This is a picture of our three-dimensional CAD model of the solar receiver and the heat pipes, along with the numerical model. The receiver contained the heat pipes, high temperature insulation, and the device that we were trying to heat. On the left, you can see a picture of the numerical result. This is called temperature profiles. Blue indicates locations where the temperature was close to 200 C or less, and red indicates temperatures in excess of 1000 C. You can see the heat pipes are operating at over 1000 degrees C and are relatively isothermal, moving energy from the concentrated solar receiver section up to the electrolytic cell. To learn the fundamentals of numerical approaches to heat transfer, we do not start with complicated problems, such as the heat transfer in a solar cavity receiver or the heat transfer in a gas turbine blade. Rather, we start with simpler problems that look more like the one sketched below. There is a saying, you must crawl before you can walk, and you must walk before you can run. You must first learn the fundamentals of the numerical techniques, and it is easy to do so in simpler geometries. Thus, we will start with problems that look like those below. In this heat transfer class, I will teach you a technique known as the finite volume technique. I denote the finite volume technique with FVM, finite volume method. The finite volume method is a numerical approach to approximate the solution to differential equations like the heat diffusion equation that defines the heat transfer for multidimensional conduction heat transfer problems. While the numerical approach is an approximation, the approximation can be made very, very good if the numerical meshes are very fine. It is important to note, however, that numerical solutions always provide an approximation to the solution to the governing equations. They are not an exact solution. Why should we learn a numerical technique? Because there are so many engineering problems for which there is no analytical solution. The big idea of the finite volume method is the following. Break up the physical system into a collection of small but finite interconnected control volumes. Apply the heat transfer energy balance equation for each volume, and then solve the resulting coupled set of algebraic equations. There is one equation governing each volume that makes up the mesh, or the collection of volumes. In so doing, an approximation to the heat transfer in the domain is obtained. The finite volume method has a number of advantages relative to alternative numerical methods like the finite element method. One advantage is that the finite volume method guarantees conservation of energy is exactly satisfied over the entire calculation domain. This is an advantage that is incredibly important when solving heat transfer problems. Another is that the finite volume method allows freedom to choose interpolation profiles between discrete points at which we store the value of the dependent variable. In heat transfer, the dependent variable is temperature. This advantage will become more clear when we look at how to derive the governing algebraic equations associated with the finite volume method. The last advantage is that we are allowed to apply different interpolation profiles when we are looking at different processes within the volumes. For example, we will apply one interpolation profile when considering conduction heat transfer, and other interpolation profiles for processes such as thermal energy generation or convection heat transfer at the boundaries. In the future parts of this lesson, we will dive into the steps required to execute a finite volume analysis in further detail.